Hello everyone, welcome to this video on electronic configuration. We are going to learn about the quantum numbers, which are like coordinates to specify the location of electrons within an atom. So let us move ahead and see different types of quantum numbers which are used for this purpose. So far, in our videos of electronic configuration, we have learned to write the electronic configuration of an element. We took the example of sodium and completed writing its electronic configuration. We also saw the distribution of electrons in various shells, and in Bohr's atomic model, we represent this distribution with such diagrams. Okay, 2, 8 and 1 in case of sodium atom. These many electrons are present respectively in K, L and M shell. Now we are going to learn about the specific difference between the electrons of a K shell and L shell, or within the L shell. If we talk about within L shell, then we are going to look at the difference between the electron of 2s and 2p subshell. Talking about within the subshell, we are going to look at the difference between different orbitals of p subshell. Okay, likewise. So we use a set of four quantum numbers to specifically pinpoint an electron within the atom. First one is principal quantum number, which identifies the shell of an electron. Second one is azimuthal quantum number, which identifies the subshell of an electron within the shell. Third one is magnetic quantum number, which identifies the orbital of an electron within the subshell. And finally, we have a spin quantum number, which identifies the spin of an electron inside the orbital. Okay, so with the help of these four quantum numbers, we can actually locate the electron within the shell of an atom. Let us understand this with the same example of sodium atom, and let us see how these four quantum number help us to identify or specifically locate the electrons. The electronic configuration of sodium is 1s2, 2s2, 2p6 and 3s1. In orbitals, we represent the electronic configuration in the form of square boxes for an orbital, and we represent the electrons with arrows having opposite direction. So let us understand their meaning and the associated terms to it. Okay. So first of all, the position of an electron is distinguished at the shell level of an atom. We distinguish two shells of an atom with the help of principal quantum number. These principal quantum number have values starting from 1. Okay, so 1 represents the K shell of an atom, 2 represents the L shell of an atom. This is how we distinguish the shell of an atom. Okay, so electron belonging to different shell can be known by indicating its principal quantum number. Now, within a shell, the electron is further distributed in the subshells. So, if there are more than one subshell in a shell, we have to distinguish between them. And this distinction between subshells within a shell is made by azimuthal quantum number. For example, In L shell, we have two subshell S and P. So this S subshell of L shell will have different L value. This P subshell of L shell will have different L value. We make the distinction between 2S and 2P with the help of different L values. Okay, so we have pinpoint the electron so far within the shell and within the subshell of that shell. Now, a subshell is divided into various orbitals. For example, p subshell has 3 orbitals. We distinguish between orbitals with the help of magnetic quantum number. Each of these orbitals will have a different magnetic quantum number so that we can identify them separately. Okay, and finally, two electrons can reside within an orbital. We distinguish between these two electrons with the help of spin quantum number. They will have different values of spin quantum number within the orbital. Okay, so each of these quantum numbers help us to distinguish at each level of division within the atom. Having discussed this, now let us see the mathematical values associated with different quantum numbers. The shell of an atom is represented by the letters K, L, M, N, and so on. The associated principal quantum number values with these shells starts from 1. For K shell, the N value is 1, for L it is 2, M it is 3, and so on. Okay, this helps us to distinctly identify a shell within an atom. A shell is divided into subshells. There are as many subshells within a shell as the N value of the shell. For K shell, N value is 1, so there is just one subshell. The first subshell is S. For L, N value is 2, so there are two subshells S and P. Likewise, in M shell, there are 3 subshells S, P, D. In N, there are 4 subshells S, P, D, and F. We distinguish between these subshells with azimuthal quantum number, which starts from 0 and goes till n minus 1. Okay, so the value of S subshell will be 0. The value of L for S subshell will be 0. It begins from 0 and goes till n minus 1. Okay, for K, n is equal to 1, so n minus 1 is 0. So it begins and ends right here. Okay, now for P subshell, it will go till 1. For S subshell it is 0, for P subshell it is 1, for D subshell it is 2, and for F subshell it is 3, and so on. Okay, this is how we distinguish the subshells within a shell. Alright, now we can designate the subshells along with shell in this manner using the n value of shell and using the name of the subshell. 1s represents the S subshell of K shell. Similarly, 2p represents the P subshell of L shell, and likewise all the other designations. Okay, now a subshell is divided into orbitals, and these orbitals are identified by magnetic quantum number. The values of magnetic quantum number ranges from -L to +L, and the number of orbitals in a subshell is equal to 2L plus 1. On using the L values of respective subshells, we will find out there is just one orbital in S subshell, there are 3 orbitals in P, 5 orbitals in D, and 7 orbitals in F subshell. Okay, now the value of magnetic quantum number ranges from -L to +L. For S subshell it is 0, so its value is 0. For P subshell it is 1, so its value ranges from -1 to +1. And we have 3 orbitals in P subshell which are identified by magnetic quantum number -1, 0 and +1. Similarly, the 5 orbitals of D subshell are distinctly identified by magnetic quantum number starting from -2 and goes till +2. Okay, and same goes for F subshell as well. Now, once we have distinguished between magnetic quantum number within an orbital, the opposite spin of electrons is identified by spin quantum number. One of the electron will have a spin represented by plus 1 by 2 and another will have minus 1 by 2. This is how we distinguish between the spins of the electron within the same orbital. Okay. With this discussion, we have concluded our series on electronic configuration. Thank you so much for watching, and please do watch all the videos related to this series so that you can have a firm understanding of this concept. Thank you so much once again, and see you in the next video.